Blue-ringed octopuses, comprising the genus Hapalochlaena, are 4 highly venomous species of octopus that are found in tide pools and coral reefs in the Pacific and Indian Oceans, from Japan to Australia. They can be identified by their yellowish skin and characteristic blue and black rings that change color dramatically when the animal is threatened. They eat small crustaceans, including crabs, hermit crabs, shrimp, and other small animals. They are recognized as one of the world's most venomous marine animals. Despite their small size 12 to 20 centimeters, 5 to 8 in, and relatively docile nature, they are dangerous to humans if provoked when handled because their venom contains the powerful neurotoxin tetrodotoxin. The species tend to have a lifespan of approximately 2 years. This can vary depending on factors such as nutrition, temperature, and the intensity of light in its habitat. The genus was described by British zoologist Guy Cockburn-Robson in 1929. There are 4 confirmed species of Hapalochlaena, and 6 possible but still undescribed species being researched: greater blue-ringed octopus, Hapalochlaena lunulata, southern blue-ringed octopus or lesser blue-ringed octopus, Hapalochlaena maculosa, blue-lined octopus, Hapalochlaena fasciata. Hapalochlaena nyerstrassi was documented and described in 1938 from a single specimen found in the Bay of Bengal, with a second specimen caught and described in 2013. Blue-ringed octopuses spend most of their time hiding in crevices while displaying effective camouflage patterns with their dermal chromatophore cells. Like all octopuses, they can change shape easily, which helps them to squeeze into crevices much smaller than themselves. This, along with piling up rocks outside the entrance to its lair, helps safeguard the octopus from predators. If they are provoked, they quickly change color, becoming bright yellow with each of the 50-60 rings flashing bright iridescent blue within a third of a second as an aposematic warning display. In the greater blue-ringed octopus, Hapalochlaena lunulata, the rings contain multi-layer light reflectors called iridophories. These are arranged to reflect blue-green light in a wide viewing direction. Beneath and around each ring there are dark pigmented chromatophores which can be expanded within 1 second to enhance the contrast of the rings. There are no chromatophores above the ring, which is unusual for cephalopods as they typically use chromatophores to cover or spectrally modify iridescence. The fast flashes of the blue rings are achieved by using muscles which are under neural control. Under normal circumstances, each ring is hidden by contraction of muscles above the iridophories. When these relax and muscles outside the ring contract, the iridescence is exposed, thereby revealing the blue color. In common with other octopoda, the blue-ringed octopus swims by expelling water from a funnel in a form of jet propulsion. The blue-ringed octopus diet typically consists of small crabs and shrimp. They also tend to take advantage of small injured fish if they can catch them. The blue-ringed octopus pounces on its prey, seizing it with its arms and pulling it towards its mouth. It uses its horny beak to pierce through the tough crab or shrimp exoskeleton, releasing its venom. The venom paralyzes the muscles required for movement, which effectively kills the prey. As with other octopoda, they have a sassy attitude when around the same species, willing to do as much as fight and kill each other to consuming the dead octopus, to even having an opinion on people, to even the environment they are within. As octopuses can open clamshells, maneuver rocks, even dismantle the filtration system of an aquarium tank. They've also developed opinions about people. One routinely squirted water down the back of a keeper it seemed to dislike. Another shot a jet of water at a light to cause a commotion. The blue-ringed octopus diet typically consists of small crabs and shrimp. They also tend to take advantage of small injured fish if they can catch them. The blue-ringed octopus pounces on its prey, seizing it with its arms and pulling it towards its mouth. It uses its horny beak to pierce through the tough crab or shrimp exoskeleton, releasing its venom. The venom paralyzes the muscles required for movement, which effectively kills the prey. The mating ritual for the blue-ringed octopus begins when a male approaches a female and begins to caress her with his modified arm, the hectocotylus. A male mates with a female by grabbing her, which sometimes completely obscures the female's vision, then transferring sperm packets by inserting his hectocotylus into her mantle cavity repeatedly. Mating continues until the female has had enough, and in at least one species the female has to remove the over-enthusiastic male by force. Males will attempt copulation with members of their own species regardless of sex or size, but interactions between males are most often shorter in duration and end with the mounting octopus withdrawing the hectocotylus without packet insertion or struggle. Blue-ringed octopus females lay only one clutch of about 50 eggs in their lifetimes towards the end of autumn. Eggs are laid then incubated underneath the female's arms for about 6 months, and during this process she does not eat. After the eggs hatch, the female dies, and the new offspring will reach maturity and be able to mate by the next year. The blue-ringed octopus, despite its small size, carries enough venom to kill 26 adult humans within minutes. Their bites are tiny and often painless, with many victims not realizing they have been envenomated until respiratory depression and paralysis begins. No blue-ringed octopus antivenom is available. The octopus produces venom containing tetrodotoxin, histamine, tryptamine, octopamine, taurine, acetylcholine and dopamine. The venom can result in nausea, respiratory arrest, heart failure, severe and sometimes total paralysis, blindness, and can lead to death within minutes if not treated. Death is usually from suffocation due to paralysis of the diaphragm. The major neurotoxin component of the blue-ringed octopus is a compound that was originally known as maculotoxin but was later found to be identical to tetrodotoxin, a neurotoxin also found in pufferfish, and in some poison dart frogs. Tetrodotoxin blocks sodium channels, causing motor paralysis and respiratory arrest within minutes of exposure. The octopus's own sodium channels are adapted to be resistant to tetrodotoxin. The tetrodotoxin is produced by bacteria in the salivary glands of the octopus. Direct contact is necessary to be envenomated. Faced with danger, the octopus's first instinct is to flee. If the threat persists, the octopus will go into a defensive stance and display its blue rings. If the octopus is cornered and touched, the person would be in danger of being bitten and envenomated. Tetrodotoxin can be found in nearly every organ and gland of its body. Even in sensitive areas such as the Needham's sac, bronchial heart, nephridia, and gills, tetrodotoxin tested positive and has no effect on the creature's normal functions. This may be possible through a unique blood transport. The mother will inject the neurotoxin into her eggs to make them generate their own venom before hatching. Tetrodotoxin causes severe and often total body paralysis. Tetrodotoxin envenomation can result in victims being fully aware of their surroundings but unable to move. Because of the paralysis, they have no way of signaling for help or indicating distress. The victim remains conscious and alert in a manner similar to curare or pancuronium bromide. This effect is temporary and will fade over a period of hours as the tetrodotoxin is metabolized and excreted by the body. The symptoms vary in severity, with children being the most at risk because of their small body size. First aid treatment is pressure on the wound and artificial respiration once the paralysis has disabled the victim's respiratory muscles, which often occurs within minutes of being bitten. Because the venom primarily kills through paralysis, victims are frequently saved if artificial respiration is started and maintained before marked cyanosis and hypotension develop. Respiratory support until medical assistance arrives will improve the victim's chances of survival. Definitive hospital treatment involves placing the patient on a ventilator until the toxin is removed by the body. Victims who survive the first 24 hours usually recover completely.